Awesome. Well, I do apologize for my voice. This is not the way it normally sounds. We'll get through this. It is an honor and a privilege to speak to you this morning about a topic that is near and dear to me, which is scientific computing, specifically vector computations. For a long time, we have had the goal of being able to write generic code for purposes of doing math, physics simulations, things of this kind. We would like to be able to reuse this code. And in some sense, the promise has been there for decades, but the reality has not quite followed. I mean, I have books that date back to the 90s, which speak of doing this in a generic way in terms of object-oriented programming that did not really deliver on that promise. Not going to name names. But today I want to talk about some things that have happened in the language in the last, well, since C++11 at least, and more so since C++20, that make it possible to do some of the things that we would like to be able to do. So here's our sort of model problem. You want to write a library that does a bunch of math operations, and you want your library to be able to use an arbitrary type. But you don't want your library to depend on, say, the headers for that type. You don't want to make it a necessity. So how do you go about doing this? Well, there are several possible approaches, and I'm going to look at a few of them. And I also want to compare like what happens if you come at this from the traditional object-oriented approach and what frustrations does that lead to. And then I'm going to show a tool that I developed that makes certain aspects of writing this kind of code much more painless. So why do we care about vector computation? Well, it's basically everywhere. And so when I say vector computation, I'm talking about vectors of real numbers, not integers or complex numbers. These appear all over the place. Certainly the AI and ML boom. Oh, there's a timer going down for some reason. My personal interests are in scientific computing, so PDE constrained optimization is one thing I'm particularly interested in. But this also has applicability in games and graphics and image processing and so forth. So the problem is, of course, and this is not specific to C++, but it's certainly something that we all have to contend with, is that there's always a trade-off between going for performance and going for abstraction. That you can write things exactly for your hardware, but then of course it's not portable. You can't extend it readily. You can't maintain it readily. On the other hand, if you go too far in search of abstraction, then you can also have other problems. So there are a number of design approaches that can be used here. And I'll just mention a couple of them. So I will be mentioning CRTP, which I assume most people are familiar with. The curiously recurring template pattern is one way to get around some of this, but it doesn't have necessarily the flexibility of what we would really like. We'd like to be able to write algorithms that work for anything that we consider to be a vector. There are, of course, expression templates. So if you've used Eigen or Armadillo or software like this, you're probably familiar with this. And if you've ever written your own expression template code, you've probably generated compiler errors that are in excess of 1,000 lines long. That's always fun to debug. And then there are, of course, other approaches involving, say, traits or function templates and policies and type erasure and so forth. Okay, so my personal motivation for this is for a library that I've worked on at Sandia for, about 11 years now, which is called the Rapid Optimization Library. It started before I joined. It is a general purpose numerical optimization software. It's focused on gradient-based optimization, though, and the original motivation was for very large problems. So things where you're optimizing over distributed parameters, say material parameters in space, and you have like a finite element or a discontinuous Galerkin discretization, and this shows up as a generally nonlinear equality constraint or a dynamic constraint, and then you formulate a constrained optimization problem for this. And my colleagues and I, when we wrote this, what we knew was object-oriented programming. We knew how to do inheritance. We did not know about, well, many things that are now possible. And there's been, there's good reasons for using object-oriented programming, at least so for portions of this kind of infrastructure. For example, most numerical optimization software, if it's in C or Fortran or whatever, you will invariably have to copy your data between, say, your application code and the optimizer. And if you have inheritance, well, then you can encapsulate that data in a class that inherits from an abstract vector class, and then you don't have to do that. And this is fine under certain circumstances where you know that the types of operations that you need to perform are somewhat constrained, sort of like typical linear vector space stuff. But then once it starts to become more exotic, you run into some difficulties. And it's flickering over there. A particular example of this would be, if you want to try to run things on a GPU. And you certainly aren't going to be doing virtual lookups, on the GPU, or certainly not recommended to try to do that. Okay, so when is object-oriented good? There's a question that came up about this earlier, and I'm not sure I'm going to be able to give you a more definitive answer. But in some sense, you want to use object-oriented programming when you have when you need to ask the question repeatedly, right? So what you don't want is to say, oh, what is this vector? What is this function? And the answer is always the same thing. That means you've probably chosen poorly. In scientific computing, this is often the case. You know this is your container type. This is what you are going to be using, and it's not going to change. And certainly, you're not restricted from making runtime decisions. It just means that you don't have this particular mechanism for performing dispatch, which is very convenient under particular circumstances. In a lot of the codes I've worked on, I've seen object-oriented programming used specifically because it defines an interface, and that was how the authors knew how to define an interface. Maybe that's the thing to do, but in general, don't do it just because you need an interface. There's other ways to do that. And I'll just say, over the years, I've seen many blog posts and so forth which malign object-oriented programming somewhat unfairly because, it's like reading recipes, reviews where somebody changed all the ingredients. You used the thing wrong and you made it a nightmare for yourself, and then it became a maintenance problem. Out of curiosity, who here has ever worked on a project where there is an object class that is over 1,000 lines long? How about over 10,000 lines long? Oof, right? This goes beyond the realm of human executive function to even keep on top of what all that stuff is. You give it to an LLM and you just blow out the context window. Happens to me too. Don't want that. That said, in defense, if you're doing the kind of thing where it makes sense, it's tough to beat, right? If you've ever tried to write your own virtual inheritance from scratch as a programming exercise, you're happy to not have to do that. Okay, so what kind of algorithms do we want to work with? So there's a motivating example. I'm just going to take conjugate gradient. So this is great because it's math. We like math. Well, I do anyway. Need to turn this thing into code somehow. Some of these symbols have direct representations in code and others do not. So the idea that a matrix is self-adjoint or that its spectrum is positive and all this sort of stuff, this is difficult to quantify in terms of code. But the fundamental operations, we need to be able to scale a vector by a number, a real number, or compute an inner product, or add vectors together, these kind of things. And be able to apply some kind of a mapping, a self-map from the vector space onto itself. So if we look at this, we need to have these kind of methods at the bottom. So inner product, scale in place, add in place. You probably want some notion of dimensions so that you can ensure that you're doing an operation that's compatible between your operands in terms of dimension. And then you need In general, you need something like clone or deep copy or allocate or whatever you want to call it, which is not mathematical in nature. Right? There's nothing in this algorithm that says, hey, you need to have some kind of scratch space, which is a little bit frustrating, but it is what it is. So what you don't particularly want to do when writing code from algorithms like this is to have to spend a lot of time accounting for all of the things that you might need later on. You'd like to be able to get them a scratch vector on demand and not have to think about, okay, well, I've used this and now I can reuse it and so on. This distracts from the whole, like translating the algorithm to code. This takes away from what you're really trying to do, which is to just write something that you can use for any kind of vector type. So here's our 5 basic operations. There are others that we can have, but I consider these to be the essential ones. So we'd be able to add vectors, scale vectors, take inner products, check dimensions, and then have some way of being able to make available space for a intermediate computation. Okay, now if you went at this from the object-oriented perspective, things get to be frustrating real quick. So you think of having a base vector class that defines a pure virtual functions for the interface, these add and scale, inner product dimension. Then you get to clone. Well, what do you do here? By inheritance, really, you can only return, well, a reference or a pointer to a vector, unless you have a covariant return type mechanism set up. You don't want that. You probably want a smart pointer. But this already kind of restricts what you can do, because you might like to stack allocate memory that you could reuse. Well, this doesn't really let you do it. Or you might like to be able to return a view or have some kind of memory arena or something like this. Okay, so let's say for purposes of simplicity that we'll return a unique pointer to a vector when we call clone, so at least that memory is managed and somebody's responsible for it. So if you think about trying to implement conjugate gradient method using this class, you'd have some kind of interface like this. You say the solution to this thing that I want to compute is X, and I'm giving it some kind of a mapping A and a right-hand side B, and maybe some parameters for the tolerance and the number of iterations. But then you go through the algorithm and you see, oh, okay, well, I kind of wanted to apply A to X and take a difference. And it becomes very tedious because now you have to do multiple steps. You have to allocate, you have to apply, you have to scale, you have to, all these things take away from just implementing the algorithm. Think, oh, okay, maybe I should add like an AXP. That's a pretty typical thing. Okay, so you go back to the drawing board and you add another method to the base class and you realize that this is probably going to be a slippery slope. Yes, so you can do this. You could provide a default implementation. All right, this would be our default implementation. So now people who want to write their own don't necessarily need to implement this, but it would be advisable because you are allocating and deallocating memory every time. And that's something you'd rather not do if you can help it. All right. So, yeah, what we'd really like to do is something where we don't actually have to say what clone does exactly up front. All that we need is a notion that clone is going to give me another vector that I can do something with, or at least give me access to a vector that's not previously spoken for by some other entity. You can look at some of these different approaches for implementing these kind of methods. I will just say, okay, object-oriented is going to get frustrating in a hurry. You can do things like CRTP or traits. The frustrating thing about these, I mean, there's a few things, but one of them is they're not completely generic. You can't really use concepts for a CRTP class or a traits class. You basically are going to specialize for a type or a dependent type. And what you'd really like to do is be able to say, I want this algorithm to be defined for everything that implements the operations that the algorithm needs. Of course, you could use free function overloads. And if many people have walked this path where you started off doing object-oriented programming and you read the advice that you should prefer free functions, and you go out and you do that, and then you realize that ADL is a problem you never had to contend with before, that can be also humbling. We'll get into that. Okay, so we heard about concepts this morning, so I'm not going to go into too much depth, but here's the idea. For each of those pure virtual functions that we had in our base class for the vector, we're going to have a concept. And the concept is just this, that I should be able to add a vector to another vector. So given some sort of mutable reference to something and a const reference to something, there should be a signature called add in place that does something and does not return anything. Okay, and how to deal with the clone problem? Well, I don't know if I want clone to dynamically allocate something or not. Well, I don't need to. So what I can do is I can define a thing called deref if needed, which basically is just a little wrapper that, so what's the issue? The issue is this: you write the algorithm and you need to know, where do I put stars to dereference things, or where do I use arrows to access methods that belong to a pointer object? Well, you don't want to do that, right? You just want to write the algorithm in a uniform way. And so whenever you clone something, if you apply deref if needed, if that thing happens to be a pointer, well, then it will dereference it. Make sure that you keep it in a scope so you don't get a dangling reference. But if it's not, then nothing happens. It just passes through, and that lets you write uniform code for both cases. So then we can write a concept for a thing that can be cloned, and a thing that can be cloned is something that I can pass to a clone function and take that result and apply dereference if needed and get something back that is convertible to the type that I started with, right? So this gives me a notion for how do I implement a clone constraint. Dimension, pretty simple. You apply a function, you pass it to a function, and it gives you an integral value number for how large is that vector. You can define a type alias to go with it. Inner product, right? You have two const references to the same type. You pass them to an inner product, and you get something back that satisfies what I'll call real scalar concept. Note on notation, I'm using _C for everything that's a concept, which is not standard, but I just find it to be easy to keep track of what each entity is that way. All right. And here we go. So scale in place, same thing. Now you need two parameters. There's one parameter that would correspond to your vector and one that would correspond to your scalar. The relationship between these two types is not specified in the concept. That's something that we will pin down more precisely later. All right, you put these things together and you can define a real vector concept. This is a type T, satisfies the real vector concept, provided it implements add in place, clone, dimension, inner product, scale in place. And that the scale in place, that second argument is now specified. The element type of the vector is what you get from performing the inner product. So this says that if I take that type that the inner product function returns, that I can scale all of the elements of the vector by that type, and that is something that's well defined. So once you have this, you have everything that you need to write down the constraints for an algorithm like CG. These are the operations that CG needed. And so now you can use this on the signature. So why do you not want to use free functions? Well, because argument-dependent lookup, really. So if you're not familiar, argument-dependent lookup is a mechanism that was added largely initially so that you could have the syntactic sugar of operator overloading and not have to be writing, scope namespace, operator, plus, all that kind of stuff that kind of undermines the whole purpose of being able to write things in that concise form. It has the consequence of looking for matching functions in a variety of places that can be difficult to keep tabs on and can lead to unexpected results. So what are qualified and unqualified names? You probably are familiar with things that have a scope on them, like in std or some user namespace, or they're associated with an object as a member function or member variable. These kind of things are qualified. Unqualified don't have that. So there are two different mechanisms that the compiler uses to identify the unqualified types. And I will apologize for the somewhat tortured metaphor. I spent a long time trying to think about which detective was better for which and did not come up with a completely satisfying solution. But ordinary lookup, as they call it, or just unqualified lookup without any specification, it looks for all the kinds of tokens, not just functions, whereas ADL only looks for functions. And the ordinary starts out locally and it works outward until it finds a match, and then it's done. Whereas ADL can actually find a number of possible candidates, and then it has to figure out, what's the precedence for these. So yeah, using declarations work, you can't turn it off if it's ordinary, whereas for ADL, you get the complete set of matches, and then you can sometimes get some very confusing compiler errors if there is a collision and there's no way to disambiguate. So this motivates what are called customization point objects. So this is a thing that looks like a function and works like a function, but is not a function. And the consequence of that is that ADL doesn't see it. Okay, so here's some examples of ADL in action, right? ADL would find a function in this case, where if I've defined my add in place, right? In this case, it would find this add in place because it is defined in the same namespace as the type, my vector of T. Similarly, it would find it if it is a friend. And this gets to be a little bit nebulous, but namespaces that are associated with template arguments. And there are a number of ways that a type can be associated, or namespace can be associated with a template argument. Things it doesn't find are symbols or function symbols that are not in this related namespace, or they're in a global namespace, but the type is not in the global namespace, and things that you only get through a using declaration. So most importantly for this talk, the other thing that they don't find are functors. So you can create a functor, which is a function object, like this, write a struct and write a template method for the call operator, and then instantiate this thing with inline constexpr, right? And I use this non-standard notation instead of tag or whatever to indicate that this is a functor, so _FTOR, whereas the instance of this object, the customization point object, doesn't have any kind of extension. So this add in place object is something that can now accept two arguments of the same type, provided the const condition is satisfied. And you can define what happens inside of this call operator here, and this would be some add in place that you define in your own library, and it is not the same as the one at the bottom, right? Because this thing, apologies. Let's see if this works, right? Nope. I can't highlight. The add in place that is inside of the call method is seen by ADL as being a function, whereas this is not seen as being a function. So there's no kind of recursive behavior here. All right. You can also simplify or condense the syntax slightly and write something that maybe looks a little bit funky, which is to say inline constexpr struct. Put it all together. That's fine. All right. So where does the compiler look for this add in place? Well, whatever your type T was, right? It will look in that namespace where that type T is defined. If T is a class, then it'll look at the namespaces that are associated with base or base classes of that T, and any kind of, if you have any kind of template instantiation, the namespaces associated with the template arguments. Okay, let's see. Yes, and then this little note at the bottom, right? So if you have no unique best fit, well, then the standard says you get a compiler error. All right. So this is a so-called traditional customization point object, which does not use tag invoke, which I'll talk about in just a second, right? That you define the interface, you have some sort of mutable reference, some const reference, call the thing add in place, and it dispatches to some implementation, right? So it relies on ADL to find this. And typically, if you don't have a function that can be dispatched to, the usual practice is to write what's called a poison pill, which is sort of a deleted function that catches everything, so you at least get a clear compiler error. Okay, so the problems with this are you can run into name collisions. Add in place is not the most unique thing possible. So you have a large project with a bunch of different dependencies. More than one of them could use the name add in place. You run into some trouble there. And you do have to write a lot of boilerplate, although not quite as much as you'll see in just a minute. If overload resolution fails, well, the error may not point to exactly where the problem is. What you want is the error to point to, the signature itself and say, well, you couldn't call this in the first place because you didn't satisfy the requirements. So tag invoke is a approach that sort of centralizes all of these dispatches to a single function that takes an additional argument that corresponds to the customization point object's type. So in this case, we have our add in place functor, and then this thing would then dispatch to a tag invoke where the first argument is an object of this add in place FTOR type. And then the user would be responsible for defining this implementation. Okay, so this does buy you a number of things, right? Cleans up the namespace. You now have a single extension point. The diagnostics can be better. You don't really pay anything extra. If you're passing things by reference, then you shouldn't be paying anything extra for this. Whether or not you get copulation if you're passing by value is not entirely clear. But let's take a look now. So here we have some sort of vector type, and we want to define something like AXB that dispatches to other stuff. So what we could do is we could define this tag invoke right here in the same namespace, and then it would be found by ADL when we come down here. Just a collection of references, which I suggest looking at. The main issue with this approach, it seems to be kind of the best thing that we have in the language at the moment. It's very cumbersome. It does result in needing to write a lot of sort of code plumbing just to connect the CPO and so on. And the compiler errors, well, they're maybe not quite as bad as expression template errors, but they can be pretty bad. So to that end, I wrote a tool which I put up on the Sandia Labs GitHub a few days ago, which is called TInCup, which is a tag invoke customization point tool. Essentially what it does is it defines a CRTP base class that you can then derive from for all of your customization point objects, and it provides a Python code generator using like Jinja templates and so forth that will automatically generate the boilerplate for you in a very concise way so that you don't have to think about it. And I'd say, think of it as kind of like how CMake makes a makefile. You just generate some stuff and then you don't touch it. So what does it look like in action? So if you would run it from, say, the terminal, you could pass JSON to it. You'd give it the name of your customization point object that you want, add in place, And then you could specify the arguments that you wanted to take. So I use this sort of shorthand that generic types get a $sign. So that means anytime there's a $sign, there's probably going to be a type name or something when it gets expanded. And if you are like me and you use Vim, you can do this even more concisely. So there's a Vim plugin for this. There's also a CLine and a VS Code plugin. So you just go into Vim and you hit :CPO add in place and type this stuff, and it generates a whole bunch of code for you. So this is what it gives you. This is not the kind of thing you want to have to type by hand over and over again. And a lot of this stuff, it's just the same from one customization point object to the next. So that's one sort of virtue of this tag invoke approach, is that you do get very uniform syntax. So I do populate this with a few things here. One is this using declaration. So this is the fallback. So if you try to call this functor add in place with incompatible arguments, well, it will check to see if they're compatible by looking for a tag invoke that can take the appropriate types. And if it cannot, then it will then call the call method in the CPO base class. And then this implements sort of enhanced diagnostics that tells you in sort of common use cases where you did something wrong, what you did wrong. All right, so each of these things can now be implemented. Each of these things are also generated automatically if you want to use them. If not, you don't have to, right? This provides all of the concepts and type aliases that you can use. This is what the actual syntax of the CPO generator does. So if you pass in like I said, a $sign, then it generates template type name. It keeps track of L value and R value and forwarding references. Keeps track of the variadic arguments and const. The order doesn't particularly matter. You can write const $T or const at $const T and so forth. Same thing with volatile. All right, and just to say this, the CPO tag there's no preprocessor black magic here. This is just basically for purposes of being able to make clear compiler errors. And being able to make it easy to grep through code for places where this thing exists. All right, so what is in the base class? It inherits from two things. There's one thing called CPO introspection, another which is called CPO diagnostics, and it implements this one variadic call operator that says, well, we were not able to find a tag invoke that we needed. Let's see what actually went wrong. All right, and this does have a potential virtue, which is that by using CRTP means that you can also use ADL to look into the space namespace. I have implemented some traits classes so that you could specialize traits classes that are in the TInCup namespace for your type, as opposed to using the standard tag invoke as appropriate for what you're trying to do. Okay. Let's see. I'm going to skip that one. All right. So here's the concepts that it generates. Checks to see if you can use tag invoke, and it will check and see if it's no throw and what the return type is for that. And then in the introspection class, it defines what are the valid argument types that you can use, whether it's no throw, what the return type is, and all of that kind of stuff. As far as the diagnostics go, the things I've implemented so far are this. If you pass in a pointer, a smart pointer, as an argument, and that is invalid because you forgot to dereference it, the compiler will tell you. It will check, and each of these things has a setting on it that you can selectively turn on and off with like CMake or Meson parameters for how much work you want the compiler to do to determine what errors you made. So if you have them all on, it will it will say, okay, you tried an argument, this is invalid. But if you would dereference it, it would actually satisfy a signature. Or you passed a thing that was const, and the signature expected something that's non-const. It will check that and tell you. Or I've only implemented it for 2 because I don't want to do it for lots of arguments, but if you put the arguments in the wrong order, it will also check and see if you'd switched the order, would it have satisfied the interface requirements? And if you have the wrong number of arguments. So these are sort of the kind of typical goof ups. And it can also do a superposition of these things. So if you pass a const pointer and you were expecting a non-const not pointer. And if you compile with C++26, then you get sort of more explicit error messages because you can use static strings in your static assert messages. I did put this, a number of examples of this on Compiler Explorer if you would like to play with it, and it shows this thing in action. So here, there's some sort of struct vector that has 2 elements of type T, and then I generate a customization point object, normalize. Just basically give me the normalized version of this vector. And it has all this, code plumbing stuff here. And then down in the tag invoke, right, you compute the norm, compute the square root of the sum of the squares of the elements, and return a vector that's appropriately scaled. And then at the bottom here, I generate a unique pointer to a vector and try to normalize it. And this generates a compiler error, as it should. But importantly, it generates a compiler error that gives you some clue of what you did wrong, not have to sift through hundreds or thousands of lines of compiler message. It says that the argument types are incorrect, and that at the bottom, so no valid tag invoke overload was found for the CPO, but there is a valid overload for the dereferenced argument. So you probably just forgot to dereference your argument. It gives you something, to act on. There's sort of more advanced features as well. So you can specify additional arguments to the CPO so that there's several ways to use this. One would be you could essentially make multiple functions, or what behaves like multiple functions for the same kind of arguments with different static string values, or you could use them as a compile or runtime switch. So if you're interested in doing like an execution policy, right, you could specify what the different execution policies are in terms of this JSON with these options, say sequenced and parallel. And this will then generate a rather large bit of code where each of these things get a different tag that is a member of the CPO class. And it will generate an array of string views that contains each of these compile time strings. And then you can use these in 2 different ways. One of them would be to use the type directly so that this defines different overloads for the methods. You do compile time dispatch, or you could also have it basically delegate to runtime dispatch so that for each of these possible values that are known at runtime, it then dispatches to a different instance of tag invoke with these different types present. Okay, and let's skip over that. So then, how can we use this to make our life easier? There's a second repo which I put up. It's called Real Vector Framework that uses TInCup to basically generate all of the different customization point objects that you need. And the core ones add in place, clone, dimension, inner product, and scale in place, but also some more advanced things like XB, binary, Unary. So this would be apply an arbitrary function element-wise to a vector, and variadic. So if you have multiple vectors that you want to use as inputs in element-wise fashion, and then a couple of things that are relevant for AI stuff. So there's a ReLU and softmax. Also implements some tools for memory management. So instead of having clone generate a unique pointer to a vector, this provides infrastructure for sort of managed memory arenas using observers and so forth. And there are some benchmark numbers on the repo in the docs directory that show that you can get, hundreds or thousands of times speed up by reusing memory arena type vectors as opposed to continuously using clone to allocate and deallocate memory. Not terribly surprising. And there's also a few algorithms that are implemented. So I've implemented the conjugate gradient, limited memory BFGS, which is an optimization method. They use line search as a projected gradient descent and a truncated CG trust region method. And there's also a few transformer models. Okay. Now, one of the virtues of this approach, as I mentioned earlier, unlike say using CRTP or traits where you have to actually specialize for each particular template parameter, is that you can use these in kind of a generic way. So anything that satisfies broad criteria, such as say stood ranges range. So that means that there's a begin and an end and a size and that it's copy constructible and so forth. That you don't actually need to implement anything. All of the methods are provided automatically. It also illustrates how you would do it for your own type. So if you have range, then the default implementation for all the tag invokes are provided in terms of things that are from the algorithm and functional headers. Right. And let's see. Right. So inner product uses numeric and scale in place. And then once you have all of these things together, you can go back and look at what did you need to do to actually write the conjugate gradient method in terms of real vector concept instead of an object. So this method, this function takes real vectors, things that provide the 5 essential components, and something that performs a mapping. So there's another concept called self-map, which just means that it maps a vector from one space into the same space. And then the implementation of this, it's actually not terribly different from what you would write if you were writing object-oriented programming. The main difference is that, have what look like free functions, they're actually functors. And that instead of having, say, obj.method args, right, you now have functor name obj and then args. Otherwise, it's very, very similar. Yeah, it looks a lot like the math. You scale in place, add in place, take square roots. I've made customization point objects for a number of elements of CMath. I will get to all of them eventually, so that you're not restricted to using float, double, and long double, but basically anything that you want that works like a real number. So like if you want to use MPFR or something like that, you can do that. This is the syntax I mentioned earlier for clone. This is maybe one annoying thing. I don't have a better solution for this, but you want to ensure that you don't get a dangling reference, so that you and this is probably the only time I would advise putting 2 commands on, or 2 statements on a single line, because they go together, right? You clone, which maybe does nothing, right? And then you dereference, which maybe does nothing. It depends. But by following this procedure, then now you don't have to worry about dereferencing or anything like that. The code becomes independent of whether things are pointers or not going in. This looks an awful lot like the math version of the algorithm that just do XB, compute inner products and scale. All right. So yeah, if you want to do unary functions, you could also use the CPO generator here. So this would just take an extra template parameter, so another $F, func, or possibly this actually should have, there should be a forwarding reference here. And then this will check and ensure that every element or the element type associated with your V is admissible as an argument for the callable F. And here's the, let's see, requires unary in place, invocable, that F can take, say, a stood ranges range value T of R, that you put one of these into F and you get one of them back. Right? And similarly for binary functions, same principle. And more generally for variadic. So if you want to have arbitrarily many vectors, right, you can write the CPO like this. And it will generate this code here. And also, yeah, so here's the implementation of like how you would do variadic transform. Excuse me. And let's see, I think that about wraps it up. Yeah, so what are my next plans from this point on? One is to basically flesh out the real vector framework more, provide more algorithms, basically going to take the rapid optimization library that I mentioned from the beginning and rework it to use CPOs and tag invoke instead of inheritance. And then as far as the CPOs themselves, I am going to try to write a Clang extension to sort of do proof of concept to show if we did have this as a native language feature, like what would it look like? How would it work? There are proposals using, say, keyword virtual or customizable or something like this in outside of a class scope that would be used to indicate that this is a function that can be customized. So now that I have the infrastructure that's implemented in terms of a combination of C++ and Python, can this all be wrapped under the hood in a Clang extension for proof of concept, and then hopefully share it and get feedback and see how feasible that is for, say, 29. Right? That's it for me. Here's the repo if you're interested.
Dumb question. Why couldn't you put the clone?
Please go to the microphone. Please get on the recording.
6:30.
Maybe a dumb question. I like your talk too, by the way. Why couldn't you just put the statement that clones as the argument in the second part of your two statement line?
Sorry, where was this?
It was the only place you had two statements in one line.
Oh,
And what
okay, yes.
There's just some subtleties, I guess, that need to be appreciated in, using the library.
Actually, maybe that was further back.
Yeah, it was close to the back.
Oh, like down here. Why couldn't you put clone inside?
Yes.
Okay.
The deref is, if needed, just put in the clone X
Okay.
instead of X underscore CL.
All right. Well, so if X is let's see. So if clone returns a smart pointer, right? And then that only lives as the argument of deref if needed. What happens to that outside of that? Sorry. Yeah. So right. So you create a pointer that only lives as an argument going into that function. Then you dereference it, but you've dereferenced something that doesn't exist anymore. It goes out of scope. So yes, I did try a lot of tricks. I tried making like a wrapper class and things like that, and I concluded, as annoying as it was, this was the most robust and least error-prone approach to ensure that you don't have like a dangling reference or anything like that.
Yeah, makes sense. Thanks.
Hi, nice talk. I just wanted to ask if so if somebody told me that I had to implement lots of linear algebra operations, my first instinct would be, okay, I have to overload operators everywhere, right? For example, and I noticed several places in your talk where that seems possible. For example, the add in place operation could be naturally done with the plus equals operator, inner products with star operator, matrix inversion with the caret operator, and so on. Was there some reason you didn't do that?
Well, why did I not use the operator notation?
Yeah.
I mean, largely just to be very explicit. And actually, I would say that is a good approach to maybe put on top of this, like as a facade. Because if you are working with, as I mentioned, libraries like eigen and so forth, right? Those symbols mean different things. That they don't do what you think immediately. They create an expression that can be lazily evaluated. And so if I say A plus B, right, what do I mean by that? Like, did that actually create a container, a new thing?
So when I've had to overload operators before, a plus operator generally allocates because it's to return some sort of R value. But a plus equals operator should never allocate a whole new object. It may have to reallocate the target. Like, for example, if you do like a matrix vector multiply that changes, that may change the dimension of the target. Right. That you may have to, or actually a matrix multiply, better example, where that may actually change the dimensions of the result. So that sort of allocation would be allowed, but not like a whole new allocation.
Right. And and that is great to have because it does make it look more mathematical. But I would, my instinct would be to put that on top, and be terribly explicit with what you're actually doing under the hood.
That makes sense. Thanks.
Yeah. Oh, if that's it. Oh, what? Okay.
Does this work with Cocos?
Yes, it does. It works with anything. It's totally agnostic. So, I mean, in a way, this kind of follows in the idea of the STL, where containers and algorithms are completely agnostic to one another, right? They're decoupled. You write one algorithm and use it for all the containers that satisfy your concept. And in fact, this is used, customization point objects are used in ranges.
Hello.
Hi.
Good talk. I had a few questions that are more general. So C++ 26, we're getting, I think, vector-like types. So your blast stuff, the matrices and stuff, are you going to be using those at all? Or
You mean like std linalg?
Yeah, the linalg stuff.
Okay. I have not used those yet. That is something I will definitely look into. How to make that compatible. I guess one thing I neglected to mention as I was talking about this is that by using Jinja templates and so forth and Python to generate this very uniform code, it makes it possible to refactor in a fairly straightforward way, provided you don't touch it after you generate it. Mm-hmm. You used a recipe to cook something and you leave it there. And then as the standard changes and other things become available to you, you have a fairly straightforward way of updating that code in an automatic fashion because you know exactly, how it conforms to design. But that is a good idea. I actually should take a look at Studlinab and see how that plays.
Okay. Also, a second question. So we're also getting reflection.
Yes.
Would you consider using that instead
Absolutely.
of Python?
Yeah, that is something I definitely want to explore as well. I haven't done it yet. So the code bases I usually have to work on are kind of stuck in C++17, unfortunately. But this is 20, but it is forward thinking, and so yes, I'm going to look at leveraging reflection.
Awesome. Sounds great.
Cool. All right. Well, we'll be here all week if anyone wants to talk.